When you're running a chemical plant, two things are king: efficiency and safety. But how do you improve a live plant without risking crazy expensive downtime or worse? Well, today, we're going to dive into how some incredibly powerful simulation tools let us do exactly that: tweak and optimize performance with absolutely zero risk.
And that right there, that's the million-dollar question for any process engineer, isn't it? You've got a hunch that a small adjustment could boost your output or get you a purer product, but making that change on a live running system, it's a huge gamble. What if you could test that theory without having to touch a single physical valve?
This whole problem really gets to the heart of what we're talking about first: the optimization challenge. It's this constant balancing act between trying to get better results and the absolute #1 priority of keeping things stable and safe.
Okay, so let's be real about why this is so tricky. A chemical plant is like this giant, complex spiderweb. You change one tiny thing over here, and you can get all sorts of unexpected problems way downstream. You could lose production, you could create a bad batch of product that you can't sell, or you could even trigger a serious safety incident. The stakes are incredibly high.
So, what's the answer? Well, you build a copy, a virtual one. And this is where simulation comes into play, letting us create something called a digital twin.
A digital twin. It's pretty much what it sounds like, right? It's a super precise, dynamic software model of your actual physical plant. It's programmed to behave and react just like the real thing. This creates the perfect sandbox for us to experiment in, to test our theories and run tons of what-if scenarios, all from the safety of our computers.
All right, take a look at this. This right here is the digital twin we're going to be playing with today. It's a super detailed simulation of a cyclohexane production plant that was built in HYSYS. Every single pipe, reactor, and separator you're looking at is modeled to act exactly like its real-world counterpart. This is our virtual playground, the baseline for all the tests we're about to run. Okay, so here's the game plan. We've talked about the challenge and what a digital twin is. Next up, we're going to get our hands dirty with two really cool tools: the data recorder and case studies. And then we'll wrap it all up by showing how the data from these tools leads to smarter, safer decisions in the real world.
All right, first up is the data recorder. Now, the best way to think about this tool is like a precision instrument for asking those very specific what-if questions. It's perfect for when you have one particular thing you really want to dig into.
And the first question we're going to tackle is a big one for this plant. If we start messing with the conversion rate in the main reactor, what exactly happens to our final cyclohexane product? Are we making more of it? Is the purity getting better or worse? And what's happening to our waste streams?
Now, the way this works is actually pretty straightforward. First, we tell the software what we care about watching, things like the product's mass flow and purity. We record our starting point, our baseline. Then the fun begins. We manually go into the model and change the reactor's conversion rate. Let's say we drop it from 99.8% down to 80%, and we hit record to see what happens. We do this for a bunch of different values to build a really clear picture.
And boom, here are the results. The data recorder lays it all out for us in this really clean, easy-to-read table. Each row shows us exactly how a specific conversion rate affects all our important numbers: how much product we're making, how pure it is, and what's going out the waste pipes.
Okay, now this is the really cool part. The big takeaway from all that data. It's not a huge shock that higher conversion gives us higher purity, but what we found is the magic number, a hard line in the sand. To meet our product spec of 99.8% purity, the reactor conversion has to stay above 99.5%. If it dips even a little bit below that, we start making a product we can't sell. We just figured out a critical rule for running this plant without risking a single penny. Okay, so that was the data recorder. Now let's switch gears and check out our second tool, case studies. And this one, well, it takes things to a whole new level. While the data recorder is great for those surgical strikes, case studies is built for wide-ranging, automated exploration. It lets us test hundreds of different conditions all at once. So, for this tool, we've got a new question. There's a stream in the process, called S8, that goes into a separator. We want to understand how changing its temperature impacts our final product's flow rate and composition, not just at one point, but across its entire operating range.
What's amazing here is how easy it is to set up. We just tell the software what we're changing, in this case, the temperature of stream S8. We tell it what we want to measure, the outcomes. Then we just give it a range to test, say from 40 up to 180 degrees Celsius, and you just hit run. That's it. The software just goes off and does all the heavy lifting for you.
And check this out. This is where you really see the power of automation.
The tool just churns through the entire temperature range, step by step, and logs the results for every single point. So instead of just a handful of data points we collected manually, we now have this incredible high-resolution map of exactly how this part of our plant behaves.
So, what did we learn from all this? Well, we found something really interesting, a classic engineering trade-off. As we heat up that stream, the purity of our product gets a little better. But at the same time, the total amount of product we're making actually goes down. Why? Because the higher temperature is causing more of our good stuff to turn into vapor and escape through another stream. The simulation made it crystal clear that the sweet spot, the best balance, is right around 80 degrees Celsius.
So, just to wrap our heads around these two tools, let's put them side by side. Think of the data recorder as a scalpel. It's for precise, manual what-if tests. Case studies, on the other hand, is more like a CT scanner, automatically mapping out the behavior of a variable across a huge range. You really need both for a complete picture.
Okay, so we've got all this amazing data. But here's the thing. Data is just data until you do something with it. This is the most important step, turning all this information into actual decisions.
You know, this quote really says it all. We're not just guessing anymore or making changes based on a gut feeling. We are now using hard data from our digital twin to build a smart, evidence-based strategy for how to run the real plant.
If you remember one number from our first study, make it this one, 99.5%. We now know, with a huge amount of confidence, that keeping that reactor conversion above 99.5% is non-negotiable if we want to hit our quality targets. That's a clear, simple rule for the operations team.
And that is the real magic here. By putting the insights from both of our studies together, engineers can now fine-tune the plant. They can make sure conversion stays above 99.5% while also setting that stream temperature to 80 degrees to get the best possible balance of flow and purity. They've boosted efficiency and quality, and the best part? They did it all in a totally safe virtual world.
So when you boil it all down, the impact is just massive. You drastically lower your operational risk by testing things out first. You crank up your efficiency by finding those perfect operating points. And you gain this incredible level of insight into how your plant actually works. It's a win-win-win.
So I want to leave you with a question to chew on. Thinking about your own work, whether it's in chemicals, manufacturing, energy, what complex system could you build a digital twin of? What's that one big what-if question you could finally get an answer to? Thanks for tuning in.